Good afternoon, everybody. And I am really happy that this meeting has not been cancelled. And I have the chance to speak about our recent researches on actinide determination in soil and sediment by a sequential separation procedure using a single DGA column. So I am going to speak you briefly about the properties of DGA, about separation of actinides on DGA, determination of actinides in radioactive waste, and then I will focus my presentation on the determination of actinides in soil and sediment samples, including sample destruction, preconcentration, chromatographic separation, and finally a few words about americium and lanthanide separation. So our goal was to develop a combined procedure for the selective separation of all actinides using a single chromatographic column. So we wanted to have a procedure that is adequate for various sample types, for alpha spectrometry and probably ICP-MS, a procedure that is accurate and sensitive, that is simple, therefore cheap and fast, so that we can analyze high activity wastes and low activity environmental samples. So for that purpose, we needed a resin of high distribution ratios and selectivities, and our choice was DGA resin. So I am going to speak a little bit about the properties of DGA resin. So what we are using, this is the product of Triscam, and it was originally invented by Horwitz as a resin, of course, and it was characterized by the group of Horwitz and many other people, including Pullman. So DGA is a diglycolamide with octyl side chains. The resin that we are using is the non-branched DGA. And here you can see just our color code for the actinides that I am using through the whole presentation. So plutonium is always red, americium is black, uranium blue, thorium green. So, and here you can see the capacity factors known from the literature as a function of nitric acid and hydrochloric. So the unique property of DGA resin is that it has high distribution ratio for all actinides from high nitric concentration and especially from high hydrochloric concentration. And it is very unique that it can retain americium, and no other actinides can do the same. So we developed a chromatographic separation for the actinides. You can read about it in our paper from 2016. The basic concept was that we load the actinides from 4 molar hydrochloric on the DGA resin, where all of them are retained, and we use a strong reducing agent, so to have tri- and tetravalent actinides only. Then we elute uranium with a dilute nitric acid after oxidation to hexavalent. So it was proven that on-column redox reactions are possible on the resin. After uranium, we strip thorium and neptunium together as tetravalent species using a complexing agent, and this is oxalic acid. And we found that oxalic acid makes strong complexes only with the tetravalent actinides. Then we can strip plutonium after oxidation from trivalent to tetravalent with oxalic acid again. And finally, americium is eluted with dilute hydrochloric. So we optimized this procedure, this chromatographic procedure, determined the eluent composition, volumes, the temperature of the eluent. For the whole separation, we use a small DGA column of 0.5 gram only. And with the model experiments, we got this chromatogram. So you can see that the actinides are well separated from each other, with the exception of neptunium and thorium, which are stripped together. And recoveries with the model solution are nice. Based on this chromatographic separation, we developed a procedure for the analysis of radioactive wastes. You can read more details again about this procedure in our paper from 2016. And a simple flowchart of the procedure you can see here. So samples typically up to 100 milliliter waste are spiked, destroyed with conventional acid destruction. Actinides can be co-precipitated with ferrous hydroxide, and sometimes this step can be omitted from the procedure, and actinides are sequentially separated on the DGA column. These are the typical chemical recoveries, which are acceptable high. So with this experience, we thought that it will be easy to adopt the method for the analysis of soil and sediment samples, but this was not the case. So we failed several times, but finally we got up with a procedure that is described in our most recent paper, and that I am going to speak a little bit more in detail. So first we did two simple tests using 5 grams of soil samples. This is method 1. We used conventional acid destruction, followed by direct loading of the solution to the DGA column. This whole procedure took about 3 days, mainly because the sample destruction was long. Then in method 2, we used fusion with sodium hydroxide, acidified the sample, and loaded it again to the DGA column. So what we found that the fusion is fast. It can take a couple of hours altogether, but acidifying the sample caused the production of a lot of silica gel that made the whole procedure slow again, 2-3 days. And you can see on the next slide the results that we got with method 1 and method 2 using reference materials. The first 2 are soil samples, the second 2 are sediment samples. And you can see that the chemical recoveries for the actinides varied, and sometimes they failed. Typically, the poor results were obtained with sediment samples. So the question arose, what can be responsible for poor recovery in certain cases? So we checked the literature, and there are a lot of possible interferences on the DGA separation. There is only one element which is really a major component, and this is iron. And we checked the major components of the soil samples, which are aluminium, calcium, and iron. And we found that one of the sediment samples can be regarded as a high iron content sample, and the other sediment sample can be regarded as a high calcium content sample. So therefore, we thought that calcium and iron can be responsible for losses. So we did batch uptake experiments to study iron interference, and all the samples were loaded from 4 molar hydrochloric, what is our load solution, and we determined the capacity factors as a function of the concentration of the reagents. The first experiment, in the first one, we studied the effect of sodium sulfide, And we found that capacity factors increased significantly when sodium sulfide was added to the sample for americium and plutonium, but it was not much affected in case of uranium and thorium. When we added iron to the samples without or with sodium sulfide, we found that the retention of americium and plutonium significantly increased, and the retention of uranium and thorium was decreased in the presence of iron. So it means that we had two completely different mechanisms. We also made batch uptake experiments to study calcium interference. So in the presence of calcium without sulfide and with sulfide, we found that capacity factors for plutonium and americium decreased significantly, and that of uranium and thorium were not much changed. But when we had calcium, iron, and sulfide together, then at elevated concentrations, we could have significant losses of all actinides. So we found out that we will include some preconcentration steps in the procedure before the chromatographic separation. And our goal was to remove the silica content, to adjust the iron concentration in an optimized region, and to minimize the calcium concentration. To remove the silica, the sodium hydroxide fusion is an excellent tool because sodium silicate is soluble and it can be filtered off the system. If we add HF to the sample, silica will form soluble fluoride complex, which can be filtered also. The addition of HF helps to remove the iron as soluble iron fluoride complex. So the major question was how to reduce the concentration of calcium. And what we found out finally, that a substoichiometric precipitation of calcium in the presence of a less soluble element, this is magnesium, is possible. So the solubility of magnesium hydroxide is much smaller than that of calcium. So we did a few tests again for the preconcentration. We added increasing amount of sodium hydroxide to a given amount of calcium and found that under certain conditions, 65% of calcium is precipitated, while the amount of calcium is reduced to 14% under the same conditions when magnesium is added extra to the same amount of calcium. And we also checked that magnesium hydroxide can retain all actinides with good recovery under the certain condition. So with this knowledge, we made up our flowchart now for the analysis of soil and sediment samples. 5 grams of soil sample is spiked with tracers. Sample is destroyed by fusion with sodium hydroxide. The fusion cake is dissolved and the resulting mixed hydroxide precipitate is filtered. At this moment, the silica gel is removed in the filtrate. Then we make a mixed fluoride precipitate, which carries all the actinides and removes the remains of silica and most of iron. And then we make the substoichiometric calcium co-precipitation with magnesium hydroxide. And then we can prepare the load solution and go to the sequential separation of actinides. With this modification, we analyzed the reference materials and we found that we got good recoveries for uranium, for plutonium, and for americium. We also know that neptunium recoveries are also quite acceptable. but the method fails for thorium. Decontamination factors are nice for all actinides, and the whole procedure can be done in 2 days, including an overnight measurement. There is a special issue in the analysis of americium by alpha spectrometry. Soil samples usually contain quite a lot of lanthanides, and lanthanides behave very similarly to americium, so finally they end up in the americium alpha source, usually making it sick. So our goal was to separate americium from lanthanides on the same DGA column used for actinides. And therefore we made a model and a test to optimize the elution conditions. So here you see the chromatogram that we got with the lanthanides and that we got with americium on the same small DGA column, and before the stripping the lanthanides and the americium, uranium, thorium and plutonium have already removed from the column. We modified the original strip solution for americium. It's a slight modification, and then we used 5 milliliter or 0.5 molar HCl. We can strip americium, and you can see that the americium fraction contains some neodymium and some samarium, and the rest of the lanthanides are removed from this fraction. According to our measurement, in one example, out of 340 microgram lanthanides in 5 grams of soil, we got only 120 micrograms in the americium source, what allowed us to get a good quality americium alpha source. So let me just summarize our results briefly. So a new procedure for the separation of uranium, plutonium, americium, and neptunium in soil and sediment samples has been developed using a single DGA resin column. For all actinides, the chemical recoveries were acceptable high, decontamination factors were acceptable high, resolution of the alpha sources were acceptable good, sensitivities were acceptable high for the routine analysis of environmental samples, and the whole analysis could be done in 2 days. So thank you very much for your attention.
Thank you very much, Nora.
Hi. So
Okay.
I'm just waiting your questions.
Yeah, so are there any questions?
Yeah. Sorry.
Yes, please. Okay, maybe.
So you want to go?
Okay, I'm not entirely sure. I didn't understand. I'm sorry.
I think it's G has John who wants to go. You want to go ahead or? Oh, okay. I've got a question. So you, after removal of iron and calcium, you improve the recovery of uranium. But does it reduce the recovery of thorium by doing that? Or thorium was poor from the beginning?
Actually, we don't know what exactly is going on. So far, we know that we did not lose thorium during the whole pre-concentration procedure. We lost thorium on the DGA column, so it just went into the effluent. So what I suspect, the last pre-concentration step is a hydroxide precipitation, a calcium magnesium hydroxide. And I think that thorium is hydrolyzed in this step, and we could not dissolve it. So I suppose that this was the reason why thorium went into the effluent. But it's systematic, we know, so we should find it happened with all our samples. So we don't know yet how to treat this problem, but this is one that should be solved.
Okay, thank you.
Is that okay?
Yeah. No, I thought if you leave the iron and calcium, your thorium recovery is better, but that's not the case.
No.
Oh, okay. All right. Yeah. Okay.
Definite. That's sure.
All right. Thanks. Yeah.
Thanks.
Okay, thank you very much. There's another question. Oh, they're piling up. Okay. Sorry, trying to get back to. So we have a question on the
chat box.
Yeah, in the chat box. It's like why 5 gram of soil. So is it to get to low activities? Yeah. So is it to get to low detection limits? Why 5 grams?
Well, we had to optimize, because normal soil samples have high uranium and thorium activity compared to plutonium and americium. And we have to plan the spiking also. And the 5 gram is something where you could get good results for low activity plutonium and the natural uranium content also. But it could vary. So.
Okay. And then there's you know that Eva Kabay, so you should know her. She was wondering if you're loading, if you're loading the actinides in reduced form. If the actinides are reduced when you load them on DGA.
So why we do it on in reduced form?
Yeah, if she understands well, you're loading in the reduced form.
Yes, that's fine. Well, in the reduced form, we had a lot of other tests. How it was originally proposed by Horwitz, that was just plutonium, adjustment of plutonium to tetravalent. But when we did this procedure using the sodium nitride, then we lost neptunium, which got into different oxidation states, and thorium was also released through the whole chromatogram. But when we reduce the sample, then from plutonium we also get plutonium-3, and the trivalent actinides are the best retained species on the DGA. So therefore, we found that trivalent and tetravalent actinides are perfectly retained, hexavalent not so well.
Yep,
and pentavalent not at all, of course.
Okay, yeah, thank you very much. Okay.
Thank you.